Friction. All right, here it is. Friction is a resistive force. It's always in the opposite direction of the motion of the object, or if the object's not moving, it's in the opposite direction of the direction the object would move if there was no friction. So there's something in all of this called the coefficient of friction. So let's talk about that. The coefficient of friction, and we use the Greek letter mu, so it's kind of like an m and a u combined if you want to think about it, but it's mu, is equal to, it's a ratio. It's the ratio of the frictional force also often written as capital F for force and little subscript f for friction, to the normal force. So a lot of times you'll just see mu equals frictional force divided by normal force. Which means, if one way of looking at this is to say that the frictional force, F, sub F, equals mu times the normal force. So this is why in some of these other problems up to this point, even though it seemed kind of pointless, we calculated the normal force. Because if there's friction involved, then this thing called the coefficient of friction times the normal force is what will give us the frictional force. Okay, so now, the coefficient of friction, well, friction between different, it is a function of a couple of things. In most, it's the two surfaces that are in contact with one another. Friction is a contact force. If there's no contact, there can't be any friction. So different objects or different materials rubbing against one another result in different frictions. For example, the frictional force of steel against steel will be different than the frictional force of wood against steel, or wood against wood, or rubber on concrete, or rubber on ice, or any of these things. Okay, so that's one thing. So real quickly, here's just from a text, not ours, but it is a text. Let me get that so there isn't so much reflection. And you'll notice that, so we've got materials, rubber on concrete, and then steel on steel dry, or steel on steel lubricated, wood on wood, wood on snow, like for skis, ice on ice. So, and we get different ones of these. So, and you'll notice there's also something in here called static versus kinetic. And it turns out that whether an object is actually already moving or not also impacts the friction. Imagine, if you will, you have been asked by your mother to help arrange the furniture in the living room. So you got the big, huge sofa. And so you push on it, and it takes, now imagine, I mean, you've done this before, most of you, I know you have. If not, go push your sofa in the living room, or some other large object. You'll notice it takes more force to get it started than to keep it going. When it's not moving, the friction force that's presenting itself as what's known as the static friction force. Once it is moving, then what you're dealing with is the kinetic friction force. So, if the net force pushing on an object, net force is to the right, then the friction force will be to the left. And that friction force, as we've seen, is equal to mu times the normal force. So the more mass that this thing has, therefore, or the more force between the two surfaces, is the way we want to look at it, is what is in there. Now the question is it the static coefficient of friction or the kinetic coefficient of friction? So, and that's, so for example, let me go back to this this one for, let's just say it was steel on steel, the dry steel on steel. So mu sub s is the static, is 0.8. Mu sub s, mu sub k, which is kinetic, was 0.6. So notice, for the same normal force, if it's not moving, the coefficient, the frictional force, the static friction force will be greater than the kinetic friction force. That's one thing. Another thing is that when it's not moving, the frictional force is only as much as it needs to be to keep the object from not moving. The only thing the friction force is going to do is to try to keep the object from moving. So let's make this really simple and easy. Okay? So here, let's take a 10 kilogram mass of steel. So it's this block of steel resting on a steel counter. So that means that the force due to gravity is 100 newtons, and therefore the normal force is also 100 newtons. And let's say it's not moving. Let's say we are pushing on it with some force, but not enough to get it moving. So the question is, how much will it push back? Well, the friction force, and this gets really complicated with the subscripts, but the friction force static maximum. So what's the maximum possible static friction force? That's the way to interpret this. Will equal the coefficient of static friction times the normal force. So in our case, is going to be 0.80 times 100 newtons, or 80 newtons. Okay, so what that means is the static friction can go as high as 80 newtons. So if we say, all right, the pushing force is 40 newtons. So let's get a table going here. So our applied force and our static friction force. So the friction static force. If the pushing force is 40 newtons, the static friction force will also be 40 newtons, just enough to keep it from moving. So we push harder. So now let's say we push with 50 newtons of force. The static friction pushes back and also increases with 50 newtons. So let's say we push more, 60 newtons. Again, back to 60. 70 newtons. It pushes back with 70. It's got up to 80, right? 75 will give you 75. You get up to 80 newtons of force pushing it. That's as much as it can do, but it will push back with 80 newtons, and the object won't move. As soon as you push with a little bit more, let's say 81 newtons, as soon as we push with 81 newtons worth of force, the static friction force says, that's it, I can't, you've overcome me, I can't do any more, and it gives up, and the object starts to move. As soon as it starts to move, it's no longer static friction. Now it's going to be kinetic friction. So now all of a sudden you're pushing with 81 newtons of force to the right, and you're only getting 60 newtons of force reverse, which is sometimes when you're pushing something really heavy, once you get it going, you almost fall forward, because all of a sudden your force overwhelms the static friction force, and the lesser kinetic friction force kicks in. In almost every case, the kinetic friction force is less than the static friction force. So that's a quick primer on forces. What do we want to remember? Friction. Friction is always in the opposite direction of the actual motion, or the intended motion in the case of static. There are two... Yeah.